So what we talked about so why do we still consider the induced force in the second term?
Why do we still consider the induced force? You mean the inertial force?
Oh, yeah, inertial force.
Yeah. To generate the dynamic equilibrium. So, what do you mean? So, you have, simply, it's as simple as this. You have, summation of forces on a single particle, right? Equal to 0 for equilibrium. And this may be constraint forces and applied forces, right? But this is the sum factor. This is indeed equal to 0. It's as simple as this. If you dot this with, this is a 0 vector, right? If you dot it with anything, it's still going to be a 0 vector, right? So I'm going to dot it with, in particular, the pressure displacement, DRR, right? And here is the main thing, is that here is the main statement of analytical mechanics, that this guy is 0 alone. The constraint force due to through the pressure displacement is alone. Then we immediately recover the principle of pressure work, that is the applied load dotted with this guy is 0, right? This is at static equilibrium. These statements are at static equilibrium. Now, if you want to make it dynamic equilibrium, you need to add another force, which is the inertial force. Right? The inertial force will not vanish here, but instead remains with you over the loop. Okay, let's start. We're ready for the midterm. So we'll do it next week, next Thursday. A week from today. We'll be in the same time, like class, but a different room, because we need it for 2 hours. It's two consecutive hours, okay? From 11 to 1. Up to last lecture. So Lagrange's equation isn't there. Today we're going to do more practice on Lagrange's equation. So I don't need anything particular from today, but you're going to need to look at the problems of today. Okay, so Lagrange's equation isn't there. It's in your midterm. So you have your particle Newtonian dynamics, you have rigid body Newtonian dynamics, you have rigid body kinematics, you have Lagrange's equation. So I told you already the 4 problems in the exam. Okay? So this is, like I said, 2 hours, so roughly each problem should be solved in half an hour. You should come up to this speed. It's a closed book, closed notes, only double-sided. Cheat sheet is allowed. Put anything you want. Equations, poetry, some inspirational stuff, whatever you like. Okay? Problems, you're free to put whatever you like. Okay? To just double-sided cheat sheet. All the equations you like, all the problems that you want to remember. So next Thursday. Okay, guys, any question about the midterm? Yes, ma'am.
Can we have it the Tuesday after that instead of next Thursday?
I'm fine. Is it majority? Anybody likes it next Thursday, immediately, or the next Thursday, Tuesday after? Okay, so it's majority. I'll change the request for the room. Okay. So I'll send you an email with the details of the midterm, the room, the hours again, and the stuff that I just told you, so that if anybody's not here, you'll be able to follow up. So let's start. Analytical mechanics. How many lectures have been we dealing with analytical mechanics? I guess 2 lectures, right? Not so long. Only 2 lectures. What did we do in these 2 lectures or 3 lectures? 1 into that 3 lectures. 2 lectures or 3? Only 2 lectures. With analytical mechanics. Not like too many lectures. Anyway, we introduced the principle of virtual work. That is summation over all the bodies. Just for your bookkeeping. I from 1 to n throughout the course. This is the number of bodies and or particles. Okay. J from 1 to f, from 1 to little n. This is the number of degrees of freedom. Your generalized coordinates. Okay. Maybe just for the sake of being self-contained here. By the way, we can deal with constraints, the number of constraints, the counter, I'll give it the name K, and it will be from 1 to m constraints. Today we're going to talk about constraints anyway. Okay? So here when I sum I equals 1 to n, this is the number of bodies. The applied loads, please, within the framework of analytical mechanics, we typically simply ignore the constraint forces because they are worthless. This guy dotted with the virtual displacement of that body equal to 0. This is at static equilibrium, right? Then we introduce the number principle. What a simple and meaningful principle is that the applied, all the forces are simply in equilibrium with the inertial forces, where the inertial force is simply negative mass times acceleration. Okay? So this immediately allowed us to write the principle of virtual work. Instead of at the static equilibrium, now we're going to write it in dynamics. So I'm going to add to this force minus mass times acceleration. So summation I equals 1 to large N, Fi, I'm going to add the minus Ma, Ri double dot, dotted with the same thing, equal to 0. This is, again, the principle of virtual work applied to dynamic problems. Any question about that? Like I said, please, if you have any question, please do never feel shy, please. Then we figured out a means of writing down this equation in a simpler way, right? We just introduced the R in terms of the generalized coordinates. So instead of getting just one single equation and factoring it, the coefficients of each dq1, dq2, dq3, no, we're going to write from the beginning an equation for each q. So summation I equals 1 to still large N, Fi minus Mi, Ri double dot, dotted with what we call the velocity coefficient, partial the velocity of each body, partial the velocity of the generalized coordinate. This is 0, and this equation is valid for all j, each j from 1 to n. So you apply this equation for j equal 1, the first generalized coordinate q1, you get the equation of q1. Then you get the equation of q2, equation of q3 immediately. This is what we call the principle of virtual power. Since we're talking with not displacement but velocity. That's a power, not work. It's just a variant of the principle of virtual work. This is what we arrived at, and then we said, you know what, there is, just by integration by parts, magically we turn it down this term into this very simple term, partial T, partial Q, J dot. T is your total kinetic energy, minus partial T, partial Q, J, equal, the right-hand side is the force dotted with the velocity still. We do have it, which we call Qj. And this is simply is what we call generalized force. We're going to talk about it in a minute. But now, the left-hand side, which was a very complicated expression, was what? Mass times acceleration, so I needed to differentiate twice every position vector of every mass I have in the problem, right? And then do a dot product of this guy with the velocity coefficient. Now, this very complicated term is simply determined from a single scalar function, the kinetic energy. Just give me your kinetic energy, I'm done, okay? I give you immediately the left-hand side corresponding to each Q, each little Q. Moreover, what's this Q? This is the generalized force. Okay? So the generalized force is two parts. One part that is polygenic, cannot be derived from any scalar function, so which we roughly call it non-conservative J. Okay? And the part that is conservative or a monogenic, so comes from a scalar function, right? So Qj is simply, if you remember, the monogenic force comes from a scalar function, the work function. Simply differentiate the work function with respect to the corresponding little q. And if your work function is quite complicated in the sense that it has time dependency and velocity dependency, which is not typical at all, it's very rare. If you found, I am aware of only one example, the Lorentz electromagnetic force. But other than that, it's typically just potential energy, okay? If not, then here is the general rule. You need to do this, d by dt, partial work, partial q, j dot. So this work function, sometimes we call it negative of the potential energy. So if you do that, you have the potential energy V, and in the left-hand side you have the kinetic energy T. We're gonna have them together because they have very similar terms. Partial T minus V, partial Q J dot, minus partial T minus V, partial Q J, equal to the non-conservative J. So if you don't have any non-conservative force, the right-hand side will be 0. And since we have T minus V all over the place, we're going to give it a name. And the name, as you may imagine, is simply the Lagrangian function. It's T minus V. So here is the first general form of Lagrange's equation that you can see in books. Partial L, partial Qj dot, minus partial L, partial Qj, where L is the Lagrangian, it's kinetic minus potential, it's not plus potential. Kinetic plus potential is your total energy, is something else. It's kinetic minus potential. Okay? This is the non-conservative load. If there is no non-conservative load, this is 0. And this equation for each little generalized coordinate, for each little q. If you have degrees of freedom x and theta, this is for one for x and one for theta. Okay? And you can see it's just turning the crank. You don't need to pay attention for most of the details. I don't need to pay attention for the frame of reference that I'm working within, right? Because I don't need to pay attention with respect to differentiation. I'm dealing with the scalar functions, kinetic and potential. So simply give me the velocity, I don't need the acceleration anymore. Now on, we will never differentiate twice again. We'll just differentiate once to get the velocity, then my kinetic is 1/2 mv squared. And you have your potential, just add them together to get the Lagrangian, I'm done. All the equations of motion will be simply derived from this scalar function, the Lagrangian. Do it for Q1, get the Q1 equation, do it for Q2, get the Q2 equation, and so on and so on. It's piece of cake. Let's do a relatively hard problem within Newtonian mechanics, doing it using simply this equation to see how efficient it is. Any questions so far?
So this Q, it's a sum of the conservative and the non-conservative forces.
Q is all the loads that
All
you
the
have.
things,
Yeah.
and you have taken the conservative over there on the left side.
Yes, because the conservative, by definition, it comes from a scalar function. So I like to have the scalar functions together. The work or potential energy with the kinetic, and this is what led to.
I'm just asking about the sign. Like conservative, it is minus the potential. So on the right side, it is minus the potential. On the left side, it comes as a plus.
Plus
So it's
potential,
again-
yes, but these terms, this was here positive, this is here negative. There is negative sign.
For the first one as well.
What do you mean first one? Okay, let's just do it for one term.
Yeah.
What's this term?
Partial W by partial QJ.
Okay, which is minus
Minus-
partial V partial Q. Goes over there to plus
Yeah.
partial V partial Q.
Yeah.
Partial T partial Q is negative, so to get it inside, I would have to have another V. Just do it
Yeah.
on your face.
So minus into minus.
Yeah, I have a lot of minuses here. Okay, so this equation, you're required to know this equation in the exam, since we, in the midterm, since we did not talk about, because this is what we did last time, but we did not talk about non-conservative load. So in the exam, I will not ask you to know this, so all the problems, the problem that will ask you about the Lagrangian equation will not have non-conservative load. So you have the right-hand side is 0, okay? So let's do a problem. Example. You know I like pendulums, so just to make it more appealing, let's add a spring. How many degrees of freedom do we have? Please, spring constants. Okay.
1.
Any problems with
2.
assessing the degrees of freedom? We don't want to miss from the first line of the problem. So you need to just give me what is your Q1 and what is your Q2. It's you who determine these, right? Maybe you're going to represent the 2 degrees of freedom by X and Y, that's perfectly fine. Or I'll just have this as R, the radial position, and theta, okay? And here is maybe my frame, I